So today, first of all, thank you all for your interest to this topic. This has been the work from the last more than 2 years. This webinar is about the electromigration of tin bismuth solder for second-level interconnect. We finished the phase 1, and we are about to start the second phase. So for today's webinar, we will report the results from phase 1 and introduce a little bit about the second phase. Because the content of the project is quite significant, so we divided into 2 parts. For today's session, it will introduce the results based on the test vehicle we developed. It's a planar geographic design. We have another one on the bottom terminated component, use that test vehicle. So for today's presentation is on the first portion. Okay. For this project, it's chaired by Dr. PJ Sun from IBM. The co-chair is Dr. Rael Espendia from Intel. Myself, Heli, is facilitating this project. Okay. PJ, can you go to the next slide?
Thanks, Haley. So Haley, should I start?
I will talk the first couple of slides, then hand over to you. Okay.
Sure.
So here is the outline of today's session. As listed there, you see we have the part 2. It's scheduled in about 2 weeks. You can register that portion as well. I know maybe the time is not very friendly to you, but just to make sure you get the presentation distributed, you can still register, and so you will be included in the distribution. I will also introduce the sign-up procedure for the second phase. Next slide. So Rael, do you want to go through this slide?
Okay, I can do that.
Yeah.
Yes, so this slide is a timeline of the project, the tin bismuth electromigration for SLI. It was started in 2020 when the low temperature solder, tin bismuth low temperature solder that was being used in some parts of the industry, the concern was raised about electromigration. You know, before that, for about 5 years or so, there was a lot of development being done, but the concern about electromigration wasn't even brought up. And then there were some papers published where it was shown the bismuth seems to migrate under high current densities to one end of the joint, and that raised the concern. And that is when we formed this particular project around late 2020 in the throes of the pandemic. And then to 2021, basically, we had the team formation and project planning, which typically occurs for most iNEMI projects. And the real experimentation and test vehicle development started very early in 2022. And that's actually still going on to some extent with the phase 1C in progress. And then the phase 2, which I think we are going to talk about today, has to do with the solder joint mechanical assessment after electromigration, because bismuth is a very brittle substance, and that's the biggest issue with tin bismuth solders. And also determining the black length and product, which is the thickness, and at small lengths you get a lot of backflow and back pressure, and electromigration stops, and we want to determine what that is for tin bismuth solders. And also under fill effect, there has been a couple of papers published about the underfill effect on these tin bismuth solders, and we want to use our technique, which PJ is going to go over to determine that. And finally, the phase 3, which is going to be next year, the electromigration. You see if we can get electromigration under use conditions. Most of the electromigration shown in the literature is with a very high current density and high temperature, which may not necessarily be the case for some certain applications like client computers. So that's what we are trying to figure out in that number in phase 3. So really the objective here is to develop a model that predicts the life of bismuth tin solders when they are subjected to mechanical, electromigration, thermal, and mechanical stresses. That's basically the objective here. Okay, you can go ahead, next slide. I think PJ, you or Haley, you might want to take over.
Yeah, this slide just show the participating members of the first phase. In fact, the number of participants are increasing. I think I will then hand over to PJ to introduce the project.
Thanks, Haley and Rio. So let me get started. So we have two ways of studying electromigration. The one shown on the left is using like a BGA or bottom terminated component solder ball. So in this approach, we can measure the resistance of the solder joint of the solder ball and thereby monitor the electromigration. But we cannot observe the microstructure as the electromigration happens. The only way we can observe the microstructure is by cross-sectioning. The approach on the right side, which is the approach we will describe today, is the planar geometry test vehicle. So in this case, we have a very thin solder joint, as shown here in gray. The thickness is 35 micron. The length can be 0.2, 0.5, whatever millimeters you want, and the width is typically 1.5 millimeters. The current flows in this case from right to left. So we can actually put this specimen under a microscope, and we can observe the bismuth atom, the bismuth moving from the right to the left and collecting at the left interface. While doing that, we can also measure the electrical resistance. So this is a very powerful technique of studying electromigration in tin bismuth solder. And also, these specimens are very easy to fabricate. So we can fabricate a dozen of these in a day in an ordinary metallurgical laboratory. And the surface of the solder is highly polished. So it's like a metallographic sample. We can actually observe the microstructure, and I'll show you that in subsequent slides. So today's talk will be on planar test vehicle. And in 2 weeks, we'll talk about the bottom terminated component approach. So today's talk is part 1, studying tin bismuth electromigration using planar test vehicle. So again, we want to study electromigration tin bismuth alloys, including the effect of adding small additions of silver, copper, nickel, and antimony, and seeing how these additions affect the electromigration in eutectic and hypoeutectic solder joints. And we'll use the planar solder joint approach. So to get started, let me introduce tin bismuth solder. So this is eutectic solder in this case, shown by this blue arrow. So composition is 58% bismuth, and the rest is tin. So when we cool this alloy just below the eutectic, we get these large bismuth precipitation eutectic structure, The gray area is tin-rich, and the bright area is bismuth-rich. So bright area is mostly bismuth and very small amount of tin dissolved in it. The gray area is is tin, which has up to about 21% bismuth dissolved in it, just below eutectic. So just below eutectic, you get this large bismuth eutectic structure. Now, when you cool to room temperature, cooling in air is not under equilibrium condition. So you essentially follow this blue line and you get to a structure that is not equilibrium. It contains too much bismuth. So the tin-rich phase contains, let's say, 10% bismuth. At room temperature, it will approach equilibrium over many weeks and get to, let's say, about 2% bismuth in the tin, and that's when you get these fine precipitates of bismuth. So we have the large precipitates of bismuth just below eutectic, and at room temperature aging, you get the fine precipitation of bismuth. So that's just introduction to this alloy. So just keep in mind the bright regions are bismuth-rich, the gray regions are tin-rich. And the gray region is the matrix, and the gray region, which is tin-rich, is more conductive. So if we pump current through the sample, it'll want to go through the gray region. It will want to avoid the bismuth-rich region, which has high resistivity. So let's look at a typical planar joint under a microscope. So this is just one view of this planar solder. Current is flowing towards the right. So this bright region over here is the bismuth that collected on the anode side. And this gray region on the left side at the cathode is tin-rich. So basically you can see that the bismuth-rich phase has electromigrated to the right. And the reason for this is electrons have mass, they have velocity, therefore they have momentum. And these electrons with this momentum collide with and transfer momentum to the atoms, and preferentially bismuth is the atom that migrates towards the right. So bismuth atoms drift in the direction of electron current, and they pile up at the positive anode, which is positive electrode, which is the anode, and that's where they collect. Now, bismuth has high resistance. So when the bismuth phase collects at the anode, being of high resistivity, the overall resistance of the solder joint increases. So we can measure the electromigration by measuring the resistance of the solder joint. So that's the theme of a project, is to observe electromigration by measuring the rate of change of resistance or rate of increase of resistance of the solder joint. So this is the view, a top view of a tin bismuth planar solder joint. So we're looking down, and the thickness of this film is about 35 micrometers. So here's copper, here's the solder, here's copper, and current is flowing in this case from right to left. So some companies, some universities have tried to fabricate this sample, and they have not succeeded. But in my lab in IBM, I too had problems making this, but now we can make, like I said, I can make 12 samples in a day, which is starting from scratch. We do the soldering, we do the grinding, polishing, and everything, and we can get done in a day. So it's a very quick way to make samples compared to the BGA, the BCT samples, which are made on our assembly line, which takes time. Okay, so here is the way we make these samples. So the top left picture is a raw card. Now it looks silverish because we have a silver flash over the copper as a solder preservative. So the copper doesn't corrode. It gives us good solderability. So we have 5 gaps, 1, 2, 3, 4, 5 gaps in this metallization. And the idea is to fill these gaps with solder that is planar. So first thing we do is we paint solder paste over this region, and then we lay a 5 mil 0.005 inch foil of copper. Now the reason this foil is curved is because when you shear the foil, it's hard to keep it straight, but we try to keep it as straight as we can. But that's okay as long as it covers these gaps. And then in the next step, we reflow the solder, in this case at 180 degrees centigrade for about 12 minutes. We reflow the solder, and then we cool it down, and here we are peeling the foil. So what we do is we hold the foil with a tweezer, and you can see the 2 tongs of the tweezer, and we rotate the tweezer like a sardine can. We peel the copper. And the amazing thing is the solder, even though it's metallurgically bonded to the copper, when we peel it, the solder stays on the circuit board. So this came as a real surprise to me. So you can see here, the solder is on the circuit board. We have removed the copper foil. And the last step is we grind this specimen, then we polish it, and we get 1, 2, 3, 4, 5 solder joints. And we can pass current in series. So we get results in one swoop. We get results of electromigration in 5 solder joints. Now we can vary the width of these, or the length of the solder joint. Length is in this direction, width is in this direction, and the thickness is into the paper. And we have tried different lengths of solder joint. Presently, we are using 0.2 millimeters. Okay, so this is what the setup looks like. So this is in an oven controlled temperature, and this is a motherboard, and we put the daughter cards with each one has 5 solder joints. We plug them into this connector on the motherboard, and we have wiring that comes out of the board. You can see the wiring coming out, and then it goes to this table, and we measure current by using shunt resistors. Now, these are huge resistors. These are like 6-inch, they're massive. And the idea of a shunt resistor is when current flows through it, its resistance just doesn't change. So we can measure the voltage across the shunt resistor, and thereby we measure the current. Now, this picture shows the data logger, which tracks the resistance of the solder joints and also measures temperature. And here is a power supply, and here is a laptop that controls the experiment. We also can put a planar solder joint in a scanning electron microscope. So this is a homemade setup shown in this picture on the right. So we have, let me describe the cross section on the left. So the daughter card, the test circuit board is plugged into a connector. So we make electrical connections, also mechanical connections. And this daughter card, of course, has the planar solder joint in the top, shown by the black line. We connect a thermocouple to measure the temperature of the circuit board. Then this red feature is a Minco mini heater, very thin heater. So you can heat the circuit board and the solder. And below that is a glass slide, and we push with the spring. So the C-clip pushes the glass slide, which pushes the heater against the circuit board. So you get good thermal contact. And this clip is to ground the solder joint, because in SCM, you have to ground the specimen, otherwise you get electron clouding. Now, these two springs are pushing this whole setup up. It's held on the right, but not on the left. So we built a clip with two screws to keep the setup down on the left side also. So right side, it goes into a connector. On the left side, we keep it pressed down with this little clip. So this setup works really good, and it's been very useful in this study. I'll show you some results. So before we go further, the big question in electromigration is, what is the specimen temperature? So to measure the temperature during electromigration, we first plot a curve. This curve is oven temperature versus resistance, but this curve, we measure resistance by using very low current, like 0.1 ampere. So this curve has no Joule heating because we have very low current passing through the specimen. So basically, what this curve tells us is, if we know the resistance, we know the temperature. So then we pump the electromigration current, and we know the resistance of the specimen, and from that we can measure the temperature. So in this case, we can see that there is, so for example, this dot at 100 degrees centigrade was a low current, and we pumped high current. The temperature increased by about 11 degrees. So 11 degrees is Joule heating. So we can do this on every specimen. So we know exactly what the solder temperature is during electromigration. Okay, one other thing I want to show before we proceed is we measure electromigration by the rate of change of resistance. So it turns out that the change of resistance, or the rate of change of resistance, is proportional to bismuth atomic flux. And I won't go through the calculation, but basically we have solder between copper lines. And when we have electromigration, bismuth segregates at the anode and increases the resistance. So in these calculations, at the very end, I'm showing the rate of change of resistance is proportional to the bismuth atomic flux. And this is basically a constant. So the resistance is increasing because of bismuth segregation, and the rate of change of resistance is proportional to J, which is the bismuth atomic flux, which is the rate of electromigration. So this is the rate at which bismuth is segregating at the anode. So this is justification for using the rate of change of resistance as a measure of electromigration. Okay, so let's do a first experiment. So early on, when we started doing electromigration experiments, we saw, lo and behold, the resistance decreases. So you would think big electromigration would increase resistance because of bismuth segregation at the anode, but we saw a decrease. So notice at 3 ampere, the decrease was for, let's say, 2 days. At 2 amperes, it was for about 5 days. And at 1 ampere, it was probably 7-8 days. So why does the resistance decrease initially? So other people have observed this also, but they have not looked into the physics of this. So let me show you why this happens. So the initial decrease in resistance is because the solder structure coarsens. So let me remind you, the bright regions are bismuth. The gray region is tin-rich phase. Over a 4-day period, at 90 degrees C, 4.4 kiloamps per centimeter squared, the structure coarsened. So now you can see the electrons find it easier to go through the gray region by moving around the bright region to get from one end to the other. So the coarse structure has lower electrical resistance. So electrical resistance decreases. But at some point, it starts going up. So why does resistance go up? So I'll show you that on the next page. Is because bismuth begins to segregate at the anode. So after 4 days, it's this thickness. After 7 days, get thicker. So that's why the resistance increases because of the bismuth segregation at the anode. This is just a summary chart. So microstructural coarsening decreases the resistance. Once the structure becomes coarse, then the resistance goes up because of bismuth accumulation at the anode. Now, what if we began with the coarse structure to begin with? So let's say we anneal a specimen and we coarsen the structure. So you can see, again, the bright region is bismuth rich, the gray region is tin rich. Now we do a 4-day experiment. The microstructure barely changes, and you can see that there is no dip in the resistance. Resistance keeps going up. So this is additional proof that it was the coarsening of the structure that caused the dip. So keeping that in mind, we made sure that we don't get confused by that dip in the resistance, that we wait for the curve to start going up before we make electromigration measurements. Okay, so now I want to get to the meat of the project, and that is, what is the effect of minor alloying additions on the tin bismuth electromigration? So people who want to design alloys, they want to study what is the effect of alloying on the electromigration. So that's the meat of the project. And I want to show you the results first. So this table it has the results of a study. So we studied 8 alloys. So 1, 3, 4, 5, 6, 9, 10, 11. And we made 4 experimental runs, 2, 3, 4, 5. So we made 4 experimental runs on 8 alloys. In each run, we studied 3 alloys. So notice we have alloy 1 was studied 4 times. Alloy 3 was studied in run 2, alloy 4 in run 3, etc. So we had 4 runs, run 4 through 5. It's the first run of the trial run, so I'm not showing those results. And the alloying elements added to the tin were bismuth, silver, copper, nickel, and antimony. No, I'm sorry, bismuth is not the alloying. Bismuth is the eutectic, so tin bismuth. So alloying elements is silver, copper, nickel, and antimony. Now the results are shown in the column on the right. I'm showing electromigration in terms of log of dr over dt times temperature divided by current density. So dr over dt is the rate of change of resistance, T is temperature, J is current density. So why am I showing results in this form? I'll explain that soon. But for the time being, assume that this is a good way to display electromigration results. But notice that since it's a log and it's minus value, so higher the minus value, the lower the electromigration rate. So if you look at eutectic tin bismuth, which is alloy 1, it only has bismuth, no alloying elements in it. So the rate is about -3 to -3.1. Now, this yellow box it's near eutectic, but it's got alloying elements like silver, copper, nickel, antimony. So notice that because of silver addition, this value is now -2.9. So this is higher electromigration. So silver addition increases electromigration. And then if you add 1.2% silver and 0.2% copper, it goes even higher. So note that small values mean higher the rate of electromigration. So silver addition increases rate of electromigration. That is silver addition to near eutectic solder. Now, hypoeutectic, which has less bismuth, like 37 to 40%. Now here, notice these values are minus 3.3, minus 3.2, minus 3.5. So this is slower electromigration. So hypoeutectic solder has electromigration at a slower rate. And antimony addition further decreases the electromigration rate. So notice without antimony, it was 3.2 and 3.3. With antimony, it went to minus 3.5, minus 3.5. So antimony decreases electromigration rate. So now these results are tabular form. I've shown you too much stuff on the table. So let's go to pictorial form. So this might be easier to understand, to digest. So in this plot, the vertical axis is log of rate of change of resistance times temperature over current density. The horizontal axis are the 8 alloys. So let's take alloy 1. The rate of electromigration is minus 3.1. Now this is a eutectic alloy. So alloy 1 is eutectic. Alloy 3, this is the rate of electromigration, which is higher because of silver addition. Alloy 4, the rate of electromigration is higher because of silver addition, and also there's some antimony in it. So we don't know what maybe the silver dominates the role of antimony. So now let's go to alloy 5. So rate of electromigration is minus 3, a little less than when silver was there. So now it's come down because there's no silver, only antimony here. So if I look at these two, look at alloy 4 and 5, if I trust these results, this is saying that silver dominates the electromigration and eutectic tin bismuth more than antimony. So antimony plays a lesser role. That's for eutectic solders. Now let's go, before I forget, there's a fifth one, which is alloys ID6. The electromigration rate has gone up very high because the silver addition is also high. I forgot to mention the right side is the weight percent alloying element. So here the silver is 1.2%, and there's some copper there. So maybe there's synergy between silver and copper. The rate of electromigration has gone much higher because of silver and maybe also copper. So that's eutectic or near eutectic cases. Now, hypoeutectic, which contains a lot less bismuth, in general, the rate of electromigration is less. But copper tends to increase the rate of electromigration in hypoeutectic, and antimony decreases the rate of. So here's antimony, here's antimony. Because of antimony, the rate of electromigration has come down. So you can say copper increases the rate of electromigration and antimony decreases the rate of electromigration. So these are our findings, but let me show you how we got to them. And there are other interesting observations we made along the way. And so before I begin, so this is a typical planar solder joint. We can observe the solder joint after electromigration. You can see that this brighter region is bismuth is collected on the left side. On the right side, this region lost the bismuth. It's become more grayish, but it's more clear in the cross section. So this is the bismuth segregation on the anode. And here, the gray region is the tin-rich region which got left behind because bismuth moved to the left. So the bright region is the bismuth-rich phase, which electromigrates to the anode, and it causes the resistance to increase because bismuth is the resistive phase. The gray region is more conductive. So when bismuth segregates at the anode, the resistance goes up. So that's why we can use resistance to solder joint as a measure of electromigration. So here is how we do the experiment. Okay, so we take a specimen. In this case, I'm showing you just one solder joint. And on the vertical axis is the resistance the data logger measures. And the resistance is in milliohms. The horizontal axis is duration of the test. So this test ran from 0 to 60 days or 50 days. So first, we had the oven temperature at about 100 degrees centigrade. Now, this is not the temperature of the solder joint because we have to add the Joule heating. So here I'm just showing you the oven temperature is at 100 degrees and the resistance shoots up and gets to this value. And so we ran this test at 100 degrees for 10 days. And then we lower the temperature to 90 degrees. So this red line is temperature. Notice the resistance dropped when we decreased the temperature. And then when we held it at 90, it increased. And then we dropped the temperature to 80 degrees. Again, the resistance dropped. And then slowly the resistance increased and so on. Now, notice that these black lines, curves, are the resistance, right? So this curve at 90 degrees is just approximately a straight line curve. But at 80 degrees, it starts to have a little dip in the resistance. At 70, the dip is bigger. At 60, the dip is even longer. So the dip lasts for a longer time at lower temperatures. So there are two things we want to examine here. One is the drop in resistance when we lower the temperature. The other one is why is the resistance dipping? Remember, I've shown you data earlier. We said the resistance dips because of grain structure coarsening. But here the grain structure is already coarse because we start at 100 degrees. So the specimen coarsens over the 10 days, 100 degrees. So this dip is not because of the structural coarsening. This is for a different reason. So what is that reason, right? So before I go there, let's talk about this drop in resistance. So that happens because whenever you take a piece of metal, its resistance will decrease when you decrease the temperature. So this drop is purely because we went from 80 degrees oven temperature to 70 degrees. But since we are using resistance as a measure of electromigration, we don't want to have temperature effector resistance. So what if we said, what would this curve look like if we were to cool the specimen in a thought experiment to room temperature? So on the right side, we are showing this curve, and this is what the left curve would be if we said, okay, what would this resistance be if I cooled the specimen to room temperature? And that's when we get the curve on the right. Now, in this curve, the big unknown is alpha. So alpha is the temperature coefficient of resistivity. And this is a very unpredictable term. This depends on lots of stuff. It depends on the defects, point defects, dislocations, grain structure. So what value of alpha do we pick? So what we do is we play with this curve, and we keep changing the value of alpha until we get a good fit. So when these curves, when these curves on the left converge into a smooth curve as shown here, we say, okay, that's the value of alpha. And typically it's about 0.0035 per degree centigrade in that range. But notice the dip still stays. See the little dip in the resistance? So let's explain this dip. So by the way, I'm spending time on this details because other people have also observed this dip, but they have said they're leaving this for future study. But there's no need for that because as a metallurgist, to us, it's obvious why we have this dip. So let me explain this. So the phase diagram of tin bismuth is shown on the right. So let's suppose our solder temperature is DCB. We are at this temperature, right? At this temperature, the amount of bismuth in the tin-rich phase is this composition C right there. So with this amount of bismuth in the tin, we have a certain resistance of that solder joint. When we cool the solder joint to GFE, the equilibrium composition will be this, will be F. So we have to go from C to F. So C is about what, 10%, maybe 6-7% bismuth. And oh, by the way, this is atomic percent. I changed before I was showing weight percent, now I'm showing atomic percent. So we go from composition C to composition F. So the tin-rich phase becomes purer. It loses the bismuth, so its conductivity goes down. So that's why the conductivity increases, resistance goes down. So that's why the resistance takes a dip. Now to go from composition C to composition F, that's a diffusion phenomena. The bismuth has to diffuse out of the tin-rich phase into the bismuth-rich phase. So diffusion takes time. So you can see over here, it took about 3-4 days to take the dip and go up. But also notice that at this high temperature, there was no dip. At 70 degrees, the dip lasted longer, 60 even longer, 70 even longer, and 60 even longer. So that's because diffusion process is slower at lower temperatures. That's why the dip is taking longer. So this is a good PhD thesis because with this technique, not only can you measure electromigration, you can also do diffusion experiments. So this is a very powerful technique. So I'm sorry for spending so much time on this because metallurgy is my favorite subject. So I love to talk metallurgy. So let's get back to business. Okay, so I have to explain why we're using log rate of change of resistance times time over J. I won't go through these calculations, but this is straightforward physics, and we end up with log of rate of change of resistance times temperature over J is proportional to a constant Q over K times 1 over T. Q is the activation energy, K is the Boltzmann's constant, and so you have the negative value here. That's why the curves are negative slope. So we're showing this solid black dots and some colored ones, solid ones. So this is for eutectic tin bismuth with no alloying element. And in this project, in this study, which we published at SMTA International 2 years ago, we compared the bottom terminated component test results with the planar solder. They're very similar, though there's an offset. And so here we're comparing two different techniques of measuring electromigration in tin bismuth alloys. And for this paper, we got the best paper award at this conference. So but these are old results. So let me show you the new ones. So I'll show you 4 charts. I'll show them quickly. So this is solder 1 is eutectic tin bismuth, solder 3 is eutectic with 1% silver, solder 9 is hypoeutectic. So you see right away that the hypoeutectic has lower electromigration rate, and the eutectic with a silver addition has higher electromigration rate, and the blue one is just the eutectic. So addition of silver increases electromigration. The hypoeutectic solder joint has lower electromigration. So we go to the next test run. So here, every time we have the eutectic tin bismuth for comparison. Now this is alloy 4, which contains silver and antimony. Alloy 5 contains antimony and nickel. So you can see that here the differences are not much, but still silver addition increases electromigration somewhat. When we run the experiment at 3 amps, at 2 amps, there's not much difference. So again, the bottom line is silver increases the electromigration to some extent. Antimony has little effect in the case of eutectic solder joints. And now this is the third run. Again, we have the eutectic, which is blue. 9 is the red one, which contains copper and nickel. And the green one contains silver, antimony, copper, nickel. So you can see the green one, which contains silver and antimony, is less, but the one that contains copper is more. So basically, the bottom line is the hypoeutectic tin bismuth has lower electromigration, but maybe copper increases electromigration somewhat. And the last set of data is for, again, the eutectic compared to near eutectic with a lot of silver and copper, and the last one is hypoeutectic. So you can see hypoeutectic seems to be the lowest, and then the eutectic, and then a huge increase in electromigration because of copper silver addition. And then this chart I showed you before. So this is a summary chart, and the bottom line is copper silver additions increase electromigration in near eutectic solder, whereas hypoeutectic has lower electromigration, and antimony decreases electromigration in hypoeutectic solder even further. So this is the conclusion, and I've already said these words in the previous foil, but I'll repeat it again. In near eutectic, copper and silver additions increase electromigration rates. In hypoeutectic, electromigration rates are lower, and addition of antimony decreases the electromigration rate in hypoeutectic solder even further. So with that, I'll hand over the presentation to Haley. Haley, all yours.
Yes, thank you. So, is Ralph still on? If Ralph, you are still there, you can talk.
Yeah, I'm still on, Haley.
Okay. Then you go ahead.
So these are the 3 phases as I had shown before in the timeline chart. And this is just a much more closer look at the here was just showing the 1C is still in progress with a couple of other solders that he's measuring for addition of minor amounts of various elements. And then we have a study on the mechanical shock for the BTC. And this is important because as the bismuth migrates to one end, and bismuth being brittle, there is expected to be a drop off in the shock reliability. And so that's what we're going to be doing in 2A. In 2B, critical product, current into length at which there is no electromigration in the tin bismuth solder joints. And C is the underfill effect that has been shown to be a positive one in a couple of presentations, but those were done on the FLI level, not SLI. So we are going to look at the SLI now. And number 3 is the electromigration model that we're going to develop and validate this with the industry use conditions. So as the schedule shows down there, we are in 1A and 1B have finished. 1C is almost at the end. Shock reliability should be done early Q4 or in the fall. Back pressure and underfill effect probably in the summer, will be finished this summer. And the phase 3 will go into the next year, 2026. So that's what we have as the schedule. Next slide. This slide is just showing you the process flow for the mechanical shock reliability assessment. So we are going to be using the BTC again, the BTC component, which is the one that a lot of power components are there in the client and servers. And those are the most at risk for electromigration because of the high current flowing through them. And so the JEDEC test board, the JEDEC B11A is the standard for shock testing. And that's the board that's shown there with 4 components on each board. That board is going to be assembled in an SMT manufacturing line. Then it's going to be sent to PJ's lab in IBM Poughkeepsie, New York, where he's going to plug it into another board with connectors and to pass current through it, so stress it. Just the corner joints are being stressed because they are the ones that fail first. And I think we have 3 levels of stressing, so we might have a little bit of migration of bismuth, for three levels of that, including the last level where you have a continuous continuous layer at one end, at the anode end. And then we test the boards, JEDEC boards on the shock table. As you can see, how the board is mounted and then shocked. And eventually we will get a viable plot. We have given example there of another JEDEC board, not this one. Another JEDEC, another DOE using the JEDEC board in a previous LTS PR project. So from these viable plots, we can extract the characteristic life and compare the various legs to see how much effect does the piling up of the bismuth at one end have on the shock reliability. Next slide. And I think, Haley, this is your end.
Yeah, thank you, Ariel. So I will speed up a little bit, given the time. So iNEMI has a process for the project development. If you are familiar with that, we do have a technical committee review to approve the project plan and also the project statement. So currently, the second phase that Rio just introduced is at a launch. It's open for the sign up. If any company you are interested, you can contact and consider the participation. Okay, next slide. So we have 2 documents. The one is a SOW, that's a project plan, and you can download from our website. And also there is a project statement agreement. It describes the project management rules, some policy, and some terms that the project team agree, and also with a list of resources that will be needed for the project, so that you can indicate where your company can contribute. Okay. To participate in the iNEMI project, it requires membership, because with the membership, there is already the legal framework available that members committed to that, so that they don't need to sign any further NDAs for share and discuss together. Okay. Next slide. So the sign up will due by the end of May. You can find the SOW and the PS from the iNEMI webpage. It's quite straightforward. If you are already a member, just fill in the participant. If you have multiple people in your company who want to join, you can just have one representative to sign the form. You don't need to sign multiple forms. And manager approval will be needed to support your participation and the committed tasks. And after that, you send a copy to me. So Grace O'Malley, she is our CTO, will do the review and give acceptance approval. Okay. So if you are not a member, if you are considering the possibility, you can contact me or any iNEMI staff in the region. I think that's all we have for the presentation content. So we will open the floor for questions. I saw several comments. The first one in the Q&A section, that case Newman asked if the initial dip in resistance will also occur in the field due to Bismuth cushioning. What is this duration and expected field if not accelerated conditions?
Yes, so the question is, how long will this initial decrease in resistance last, right? So that depends on temperatures. So if it's these curves show that if the solder is at 90 degrees C, then it lasts for maybe 1 or 2 days. At 80 degree, 85, a little longer. So I think this is just maybe at 60 degrees, it might last for a week or two. So maybe we shouldn't rely on this decrease in resistance. So at some point, it'll start increasing because of bismuth segregation. Any other questions?
Yeah, not
Did
sure
I answer the question
have...
right?
Case, you can unmute if you want to talk. Okay, I will read other questions. Tom asked the original activation energy chart indicated 0.92. All the newer ones have drifted upon to 1 time or 1.2 times. So any thoughts on the shift?
Okay, so let's see. So you're referring to this plot? Oh, I see. So these ones.
Yeah, your planar joints were 0.92, and all your new ones with the eutectic control are 0.97 or higher now. I can understand the few ones. But...
Yeah, so this is within the limits of the experimental error. So 0.9 and 1.0, I would say they're pretty close, you know.
Well, we'll go to the next page because I think you start approaching 1.2, 1.16. So where do you draw the line, I guess is my question.
Where do I draw the line in terms of
experimental error? You know, this would say it's 0.9 plus or minus 0.2.
Yeah, I would say plus minus
or more.
0.1. Yeah, true. Yeah.
Okay.
So, you know, the thing is that tin bismuth alloy is it keeps changing with time. So the structure keeps changing. So that probably has a lot to do with it. So I think by this typically in metallurgy, activation energies have good spread because of metallurgical variability. So these results are pretty good, you know.
Next question is from Saran of Nokia. He asked, what are the reasons for selecting particular metals for alloy? Were there any prior studies supporting the higher or lower electromigration?
Okay, so the question is why these alloying elements in this concentration? Why this concentration? These are commercially available alloys. So we did not make these alloys. So these are alloys from companies that participated in the project. So they gave us these the solder paste.
In fact, there is another iNEMI project on the low temperature solder reliability, processability and reliability. There are several alloy comparisons included in the experiment. The major purpose to adjust the dopant is to improve the mechanical or some reliability performance, or even so the industry developed different comparisons. So as PJ mentioned, those are the commercially available alloys. So we would like to see how they perform to the electromigration. Yeah. Okay. Another project is from Dave. He asked if we observed this resistance drop by simply aging the solder without any current at all.
So the question is, let's see, let me just go. This resistance drop? So what's the question?
Yeah, if the resistance drop by simply aging the solder without any current. If no current pass through, will there be a resistance drop?
There will be. So resistance drop is because of the structure coarsening. So the structure will coarsen because the structure is coarsening because of temperature, not because of current. So I think current might play a secondary role, but the coarsening effect is because of temperature. So this is called Oswald ripening. So this is a well-known metallurgical phenomena that does not require current. So that's the answer.
Okay. I think another question is about it's from Michael Mayer. Any idea about what the change in lifetime or allowed maximum current for minus 3.5 compared to for example 2.7 log TOG vector?
Right. So that's the advantage of this technique. So for example, so let's take this just eutectic, pure eutectic, the blue line. So the blue line tells you, so let's suppose you say your solder is at a certain temperature, let's say this temperature. By the way, on this scale, this temperature is lower than that temperature. So this temperature is low, and you also have a certain current density. So if this is a temperature, then we draw this line, we get this value of dr over dt times temperature divided by J. We know the temperature, and you know the current density is, so we can measure dr over dt. So for any temperature and current density from this plot, you can measure dr over dt, and that tells you after so many years what will be the increase in resistance. So and Okay, so let's look at another plot. So let's look at this one. So let's say this is the temperature. This alloy will have this electromigration rate, and this green one will have this electromigration rate. So you can calculate the lifetime for this alloy using that value, and for this alloy using that value. So you can see what the difference in lifetime is, So that's a straightforward calculation, something I've not done, But by the way, this is a log scale, so this might not seem much, but a log scale is a lot, right? It's not, so it's probably half an order of magnitude,
Wonderful.
Yeah. So I prefer these plots to viable plots because viable plots don't have as much information as these plots do.
Okay. Any other question? If you want to talk, you also can unmute yourself. Okay, I want to remind everyone there is a second part of the webinar to report the results that we achieved by using the BTC test vehicle that's set up. In that experiment, we adjusted the height of solder joint. We also tested with different current density in the surface finishes and compared with the SEC. So that portion of the webinar will be held in 2 weeks on May 13th or 14th, depending on where your location is. So if you are interested, you can register that one as well. Okay, before we end, any additional question, comments?
Yeah, hi, PJ. This is Jay Krishna. I have a question. Basically, so given the data points what we have as of now, so what is the percentage or maybe the electromigration range or percentage of a resistance drop or a resistance increase is going to be concerned majorly on the performance of the product? I think there are other factors that are influencing. But what is there any cutoff or is there any specification that we are trying to zero down, wherein that is going to be a trigger for both mechanical failures and performance related challenges? Any data that is available still today?
So are you asking how much resistance increase is acceptable?
Yeah, resistance increase is acceptable. At the same time, bismuth migration towards anode, that is going to cause some mechanical weakening of it's going to be get brittle, right? So will there be any cutoff beyond which it's going to be troublesome for the product mechanical reliability point of view?
Yeah, so maybe Rio, you can talk to that. That's the next phase of the project.
Yeah, Rio, I think he's dropped.
But Rio dropped. So maybe
yes,
so that's the next phase of the project. Yeah, sure.
Yes.
Sorry, Haley. Go ahead.
Yeah, it's the same answer. So for the brittleness of bismuth, in fact, we had another project I mentioned on the reliability performance, processability and reliability. We studied the mechanical shock and the thermocycling performance. But in that project, we didn't collect the data or study the electromigration effect. So in this phase 2 of this project, we will study first do the electromigration to search to achieve different electromigration rate, then do the mechanical shock, then correlate the reliability performance with the electromigration rate. That's the target.
Yeah, thank you. Thank you.
Okay. Any other questions? Okay, if not, I would like to thank you again for attending this webinar, and I hope we have the opportunity to work together or communicate further. And thank you, PJ, for the presentation and the great work.
Thanks,
If you guys get any other questions, you always can contact me, reach